Good morning. Today we're going to talk about the chain rule as part of Unit 4, Part B, Calculus 30. Just kind of starting with a little bit of a back check with what we can differentiate, what we can find the derivative of. The first two are examples of questions that we have already done in terms of learning how to take the derivative. The first example, y is equal to the power or the square root of x. That is something that we could take the derivative of. We would have to change it to an exponent, but we would be able to find the derivative just quickly using that power rule. The second one, again, we have taken the derivative of individual terms like this. We could find the derivative of each of these individual terms, both using the power rule. Now, unfortunately, when you combine these two types of functions where this x cubed plus 4x squared is inside a square root, we haven't got the skills yet to figure out how to find the derivative of an expression like this or an equation like this. So I'm going to come back to this one once we go over what is the chain rule. Now, to begin with, I'm just going to use an example, another one where we have got a variety of methods to figure out the derivative. Here is y is equal to, and in brackets, x squared plus 1 is being squared. So if we were to attempt this question, we have a variety of ways that we could find the derivative. One way would be to expand before we can do any derivative. We would end up having x to the power of 4, 1x squared plus another x squared, we would have 2x squareds plus 1. If we were to look at it from this perspective, again, we could use the power rule, term by term, to find that the derivative would be 4x cubed for the first term, 4x, and the 1 would be a 0, and so that would drop away. Power rule works just fine. We could use the product rule. I wrote it as two factors being multiplied together. Instead of expanding this time, I could use the product rule, where we would find the derivative, taking the derivative of the first, leaving the second, plus leave the first, and the derivative of the second. And we could simplify that so that we could compare it to this method. We would have 2x squared plus 2x. Multiplying this together, we would have the same 2x cubed. 2x cubed. Another 2x cubed plus 2x when we multiply into the brackets. And you can see very quickly that we would have 4x cubed and 4x, the same as what we had in this method. Now, what if this power was bigger than 2? Would we have the ability if it was a power of 3? Yeah. 4, 5, 6, 10, 20. That becomes a little bit too much for using these rules. So what we're going to do is figure out what the chain rule is, and then we'll go back and take a look at applying that chain rule to these examples. So what exactly is the chain rule? The chain rule sounds something like this. If you have a function, f of u, and that is differentiable, differentiable function of u, meaning that we could take the derivative if the function was in the variable u, and if that function that we have u is actually another function, and it is also differentiable of x, so this is in variable x, then what we would have is something where we would have the derivative of the main function, the outside, in terms of u, first of all, and then we would have the derivative of the inner function, the u, in terms of x. Because ultimately what we want is the derivative of a function y but in terms of x. Now this goal of getting a derivative with respect to x goes back to the fact that when we talk about derivative, we're talking about slope. We want to have the derivative with respect to x, a derivative of a function y with respect to x. So other variables kind of fill a spot, but ultimately this is our goal. So if we were to use the actual functions and in terms of x, it would look like this. No u's this time. If we had a function f of g of x, which is kind of like the first example where the square root, and I'll go back and look at that. If we were wanting to find the derivative, we would take the derivative of the f function, leaving the inside function alone, meaning that we're going to focus on what's on the outside. Can't ignore the inside though, so after we're going to take the derivative of the inside. Now, if it got really wild and crazy and we had a function inside of another function, was inside of another function, again, to find the derivative with respect to x, we would start on the outside function, find its derivative, leaving the inside alone. Moving inward, we'd find the derivative of the next innermost function, leaving the inside alone, and finally at the end, taking the derivative of the most inner function. And so when we talk about the chain rule, we should be seeing some kind of a function that's inside of a larger function. So if I were to go back to the example we were just looking at here, if I were to talk about this f of g of x, the inside here, this x squared plus 1, would be like the g of x. The g of x that's on the inside would be like our x squared plus 1. The squared that's around the brackets is like the outer function. That is our f of x. And so when we go to take the derivative using the chain rule, I'm going to follow this pattern. I'm going to take the derivative of the outside, which in this case, oops, I didn't need that bracket, is the squared. If I had something on the inside and I wanted to use that power rule to bring the 2 down, I'm going to ignore the inside for a second, and the power would drop by 1. That's the derivative of the outside. We are going to leave the inside alone, so what I had in brackets here, I will continue to bring that down. But I can't ignore the inside, so I'm going to have to multiply to the derivative of whatever's on the inside at the end. The inside, the x squared, becomes a 2x, and the 1 becomes a 0 and drops away. So if we were to talk about the derivative using the chain rule, on the outside, these two smaller pieces that are multiplied together would become a 4x. That would be multiplied to this x squared plus 1. And if I were to continue to simplify this, that become 4x cubed plus 4x, just like we had with the other ones. So this is using the chain rule. And again, the idea of the chain rule is that we have a function inside of a function and that we need to start with the outside and work our way in. So I'm backtracking to the very first example that I had given, this one. This is an example of a chain rule kind of question. Now with this one, again, similarly when we've had radicals in the past, I need to have it as a power, and so the x cubed plus 4x squared has a power of 1/2. And this is another situation where we wouldn't be able to expand. How do we write out a half of these brackets in terms of an exponent? And so we need to use the chain rule. So the derivative in this particular case, again on the outside, the half is going to come down and the power is going to drop by 1. We leave the inside alone while we deal with that outside function, but we'll multiply by the derivative of the inside afterwards, and that becomes a 3x squared for the first term and an 8x for the second. And that entire function is being multiplied to these three, or these other two factors, I guess you could say. So how do we write our answers so that it is simplified, logical, cleaned up? You'll often see the simplest of our factors written first. The half is fairly simple. This next factor over here, I would assume, is going to come next. It doesn't have any power that is over it. I call them, it's not quite so crazy. Whereas the factor with a negative half exponent is one that becomes a little bit more complicated, and it seems like the complicated ones stay at the end. So how do I decide I'm finished? There's lots of things that you could do. This is a very good answer right here, simplified. We are going to see things left as factors. We cannot expand into something that has a power of a negative 1/2, so we wouldn't do anything more with that. But you may see the 3x squared plus 8x on the top. You may see the 2 and the x cubed plus 4x squared move to the bottom, with its power of a half becoming positive. You may see the answer rewritten with a radical instead of a power of a half. All three of these are perfectly fine answers going forward. Okay, so that's the chain rule. Just gonna flip through and we're gonna find a couple more examples of things that we can do. This one here. This one, again, is a good example of a chain rule. Sometimes people are confused. Well, how do I know if it's a chain rule or how do I know if it's a product rule? Because I do see something being multiplied. I see factors being multiplied. The easiest way to decide if it's a product rule as compared to a chain rule, a product rule has to have variables in both factors. And so in this particular case, we don't have variables in this front factor. It's only in here, so that's kind of an indication that it's a chain rule. So derivative of the outside is how we start with a chain rule. That means that that power of 11 is going to come down and multiply to the 22. Again, the inside we're leaving alone and we're dropping the power by 1. That's the outside function. Leaving the inside alone temporarily, and then we'll deal with the inside function at the end. And again, the entire function, when we take its derivative, the 2x and the minus 3 is going to be multiplied at the end. So the derivative, I would say, if we're going to talk about how it's going to be written in final form, that 22 is the simplest of my three pieces, my three factors. The 2x minus 3, and then that x squared minus 3x minus 4 with a power of 10 is going to be left last. Again, that is a perfectly fine answer. We're not going to be expanding a power of 10. Even multiplying the 2 inside is not, the 22 is not necessary. So that would be perfectly fine as an answer to the derivative of that function. Okay. One more. Well, maybe. We'll see. I got a few. This one. This is another example of a radical. Before I'm ready to take the derivative of this cube root function, I need to write it as a power instead of a radical. So the x to the power of 4 minus 5x squared would need that power of 1/3 instead of the cube root of 3 on the outside. And again, now that it's in power form, we are ready to take the derivative, dy dx this time. That's the notation I'm using because they gave me a y. The outside, the 1/3 coming down, x to the power 4 minus 5x squared is left alone on the inside while we drop the exponent by 1 and the derivative of the inside. So the 4x cubed for the first term minus 10x for the second term. And again, how would I leave this as a final answer? Again, the simpler stuff, you may see them take out a common factor here, because that's going to be kind of an important step going forward, is factoring these derivatives as much as possible. So you may see, I'm going to do two steps at once here. I'm going to move the factor out the front, and I'm going to take the common factor out. There's a 2x, leaving a 2x squared minus 5, a 3 in the bottom, and there is this x to the power 4 minus 5x squared with a negative 2/3 at the end. I would say that that probably is a perfectly fine answer. You may see the negative exponent move to the bottom, along with the 3. This is the advantage of all these factors being multiplied and divided together. There's a lot of flexibility in terms of moving things around. Not so much when you have terms that are added and subtracted together. So that again is a perfectly fine answer. Okay, now with some of the questions, they will talk about the first line of the derivative. So if you were asked just to do the first line of the derivative, this first step would be enough to say that you were done, just to get the pattern and that sorted out. I think I had one more. This one here, again, initially it may look like a quotient rule to find the derivative of this function. Again, possibility, but with this question, what I can do is do a little bit of simplifying to the function before I take the derivative. For example, the denominator, instead of the radical, write it with a power of 1/2. Maybe I don't want to leave it in the bottom. I'd like to move it to the top with the 12. And again, because of the multiplying and dividing of these factors, that's easy to move. And of course, when I move the power of 1/2 up, the sign changes. And now we're in a good position to take the derivative using the chain rule. Again, I don't have any variables in this first factor, only in this one, so this makes a good chain rule. Multiplying on the outside, dropping the power by 1. Again, the inside is left alone until afterwards, and I take the derivative of the inside, 6x squared, and the minus 5 becomes a 0. In terms of a final answer, these two single terms can be multiplied together, and your factor with the negative 3/2 exponent can stay at the end. That's basically the chain rule. Chain rule using lots of elements of things that we know already. Lots of power rule built into this, but working on the outside first of all before we tackle the function that's on the inside. That's it for today. That's the chain rule.